Hi, I'm Joonhyung Kim, and this is the second oral presentation for Fourier optics. I'm going to talk about Fresnel diffraction and Fraunhofer diffraction. This presentation is divided into 4 parts. These are contents of my presentation. First, I'll briefly explain the Fresnel and Fraunhofer diffraction theory. Then we will move on to MATLAB simulation about 2 diffraction patterns. Unlike last time, I'll compare 3 different ways to make Fresnel patterns in MATLAB. Lastly, we are going to look at the summary of results. To explain the Fresnel diffraction, let's start from the Huygens-Fresnel principle in rectangular coordinates. The Huygens-Fresnel principle can be written as equation number 1, and R01 written at equation number 2 is given exactly in rectangular coordinates. Then, there have been 2 approximations. One is the approximation inherent in the scalar theory, and the second one is the assumption that the observation distance is much bigger than lambda. So we can rewrite R01 like the equation number 3. The Fresnel diffraction means the Fresnel approximation to diffraction between 2 parallel planes. Equation number 4 presents the Fresnel approximation, and this equation is expressible in the convolution form like number 5, and here the convolution kernel is h as written at number 6. Another form of equation number 4 is found if the exponential term is factored outside the integral sign, the principle written at number 7. The Fourier transform of the product of the complex field just to the right of the aperture and a quadratic phase exponential. In addition to Fresnel approximation, the stronger Fraunhofer approximation is satisfied, then the quadratic phase factor is approximately unity over the entire aperture. And the observed field strength can be found directly from a Fourier transform of the aperture distribution itself. Thus, in the region of Fraunhofer diffraction, equation is written like number 9. There are observable differences between Fresnel and Fraunhofer diffraction. In Fresnel diffraction, the viewing screen and aperture are located close together. And as the separation between the screen and the aperture increases, the image of the aperture becomes increasingly more obstructed. In Fraunhofer diffraction, the viewing screen and aperture are separated by large distance. As the separation increases, the size of the pattern changes, but the shape is not changing. Chapter 2 and 3 is about MATLAB code explanation about Fresnel and Fraunhofer diffraction simulation. There are 3 ways to make Fresnel diffraction patterns with MATLAB. First, we can use Fresnel integral as shown on the top. Second, angular spectrum method can be used by adopting this equation as h. Lastly, convolution method can be used similarly if we take last equation as h. I'm going to implement these 3 different methods using the same aperture and compare them. Let's see the Fresnel integral method. In MATLAB, define the function named square aperture. The variable a means Fresnel number for diffraction, and I generated x, y points in range of this. Then I used Fresnel function as Fresnel number. Next variable zx and zy mean complex field distribution, and f means intensity of wave field. In Fresnel number is lower than 1, variable the intensity f needs additional computation. To make video of the patterns, varying the Fresnel number so that we can see the diffraction patterns depending on the distance from the aperture plane. This is the results of the field diffraction depends on the distance. Let's check the video. Next one is angular spectrum method. In MATLAB, make the square aperture like this and define h as shown below. We can get the diffraction pattern as using right code to making video. This is the diffraction pattern obtained using an angular spectrum method. The third one is convolution method. The aperture is same as last time, and we have to change the variable h for convolution method. This is the diffraction pattern obtained using a convolution method. Let's compare three ways at once. The images look quite similar, but they are all produced in different ways. For more understanding, I made a special aperture and checked the Fresnel diffraction pattern by using convolution method. I entered the input parameters like lambda and so on. To create an aperture shape, the cross aperture made by my classmate was slightly modified. The picture on the left is an aperture I made, and the diffraction pattern on the right is captured as a video. Let's check the video. Next item is Fraunhofer diffraction simulation. I brought a snowflake image, and for using this as aperture, we need to reverse the matrix. We can get the diffraction pattern simply as a result of best Fourier transform of the aperture. The picture above is an aperture made by reversed matrix, and the bottom side is diffraction pattern. Using the code on the left, the image can be retrieved to the MATLAB. This image is made into an aperture, and the fast Fourier transform is applied to identify diffraction patterns for moving aperture. This video is pretty funny, so feel free to watch it. This is the summary of results. I designed square aperture and compared them in three ways to make Fresnel diffraction patterns using MATLAB. And I made a special aperture and checked the Fresnel diffraction by using convolution. In Fraunhofer diffraction, I convert the snowflake image and use FFT to get diffraction image. Lastly, we can get the diffraction video even if we want to use moving aperture. The last page is the list of documents I refer to. Thank you for listening.